I am happy to introduce our next speaker, Robbie Dyer, a DevOps consultant at Eficode. Robbie's talk is about cost-efficient ML model training using GitLab CICD in the cloud. Data scientists are not usually the first group that comes to mind when thinking about DevOps and cloud-native practices, yet they create software and oftentimes consume large amounts of cloud services. In this talk, Robbie shares his experience, results, and learnings from his journey to enable data scientists to do machine learning using DevOps and cloud-native principles. There's a lot of great detail in this talk. Let's dive in.
Hi, my name is Robbie Dyer. I'm a DevOps consultant based in Copenhagen, Denmark. I'm originally from the UK and I started my career as a web developer before moving on to managing cloud infrastructure and then progressing to bridging the gap between the two as a DevOps engineer. I've now been a part of Eficode in Copenhagen for nearly a year. Given that they've been kind enough to let me be here with you today, it'd be rude not to at least suggest you head to eficode.com and see if we could be of any help with any of your cloud or DevOps needs. I've also got some fantastic training, which I highly recommend. Today I'm going to be sharing my experiences with creating machine learning model training pipelines using GitLab CICD. I've been working with some data scientists and engineers at a client on this for roughly the last 6 months. We've had great results from the work that was done, and whilst the system we've created is still far from ideal and finished, we've already learned many lessons, progressed fairly far, and I hope this story might inspire some others to take the same journey. The reported outcomes of this project were pretty positive from all sides. I personally felt like I learned a lot. I always enjoy being pushed outside of my comfort zone, and it keeps work interesting. The data science and the engineering teams have both been very happy with the increased ease at which they're able to go about their work. The heavily decreased training times have been reported as another great benefit. And also people love learning new skills. And this really proved that DevOps practices do belong in data science. We've actually even had one of the members of the data science team move over to the DevOps team to help create more cross-team collaboration and further push DevOps practices out across more areas of the organization. The business was happy both with the progress on modernizing the platform and with the increased ability for the data scientists to innovate and derive value from their data. The theme of this event pairs rather well with my talk today. I certainly wasn't sure I belonged in the world of data science at first. Prior to starting this project, my knowledge of machine learning and data science was limited to a couple of neural network and machine learning courses I'd done at university, but I'd never covered any projects such as this in the wild. As a DevOps engineer from a software engineering background, I always felt at home with developers, so this new environment was certainly a little out of my comfort range. So let's start by briefly going over the ways things were and why this project came about. Previously, the data scientists had been relying on their development workstations compute resources for most ML training tasks. These workstations were running as VMs in the cloud, but it was still a far from ideal setup. I've also heard rumors of live systems being hosted on these workstations, and that certainly wasn't going to fly going forwards. The previous setup had rather a large number of downsides. The workstation VMs were having to be left on 24/7, whilst models were trained overnight or over the weekend. This added costs both in inefficient use of their time and added frustration for them, and I'm sure didn't do anything good for their productivity. Given the workstations generally weren't particularly powerful for obvious cost reasons, this also meant that nothing moved particularly quickly and iteration of models took much longer. Also wasn't possible for individuals to work on multiple models at the same time, and I'm sure it didn't do anything good for the responsiveness of their workstations whilst they were training. Another issue was that there was no single place to look when issues arose, and relevant logs weren't persisted. There was no audit trail either. So, as you can imagine, the desire from the business was to make things more efficient and to keep the data scientists happy and productive. There was a strong requirement for training to happen faster, which in turn would allow faster development of new models. We needed a standardized pipeline and set of tools which would allow new libraries to be experimented with easily. They also wanted some better tracking of operational expenditure, and there was also a desire for more cooperation between the data science, data engineering, and the platform team, i.e. DevOps, so that further developments to the platform could be driven by the right people. The requirements certainly weren't the easiest part of the project to pin down for me. I had very little knowledge of what was being done and therefore what we'd need. As with all projects like this, the requirements certainly changed a fair amount as we experimented and progressed, but we had to start somewhere. So we knew we'd need some storage for artifacts. As we were on Azure, Azure storage was an easy win here. With AWS, there's S3, or GCP, there's their cloud storage. So other cloud providers have offerings as well. Database and stream access was needed. So we needed some form of secret management. Luckily, GitLab CICD has variables built in, and we also did look at using Azure Key Vault in combination with GitLab CICD variables and service principals. We need a good range of VM sizes for different tasks. We knew we wanted to be able to do both CPU and GPU based training, and we weren't sure of what instance sizes would be best. Therefore, we needed it to be pretty easy to experiment with different sizes of virtual machines, and especially in the initial stages. We also needed a Docker image registry, as we needed to store our Docker images. We were already using Azure Container Registry for other teams, so that was another easy win. I believe AWS and GCP have their own versions of those as well. We needed some form of monitoring and logging for diagnosing issues, and we also wanted performance metrics to make sure we were getting the maximum utilization of the infrastructure we provisioned. As the data being used to train these models was sensitive and personally identifiable information, European data laws are pretty strict, so we were limited to self-managed systems as the client was unkeen on this data being passed to third parties or any external systems. So the obvious choices for orchestration in this instance was either GitLab CICD or Jenkins. Jenkins does provide additional flexibility and plugins, but the requirements in this case were already met by GitLab CICD, and the overhead of configuring and managing Jenkins was just undesirable. GitLab was also being used organization-wide for repository storage, and GitLab CICD was also being used by other development teams. So these were further attributes that supported choosing this option. Having chosen GitLab CICD as the pipeline tool, the next step was to decide how to achieve the compute requirements we needed. GitLab runner executors can be ran either using Docker, Docker+Machine, or Kubernetes. Azure Kubernetes service didn't support node pools of 0 at the time. This would have required creating node pools of expensive virtual machines with specific taints for each type of job, and we wouldn't have been able to scale them down to 0 when they're not in use or not automatically, which, as you can imagine, is not particularly efficient use of money. We were already using Docker-based runners along with Docker-based executors for code deployment pipelines. This obviously wouldn't have worked for the compute requirements we had for ML training, but it did mean with minimal effort, we were hopeful we'd be able to create new instance-based executors using Docker+Machine and the Azure driver. Using Kubernetes would have added additional difficulty in testing new instance types as well, as we couldn't quickly add new instances in the same way you can with Docker+Machine, and it would have required creating new node pools and taints, which for a POC is not particularly desirable. We did have a slight concern that Docker+Machine has been moved to maintenance mode, but GitLab have forked this, and I believe are still continuing to support it. But I suspect we will eventually move away from Docker+Machine as the executor and move likely to Kubernetes, but it was a very good starting point. As you can see from this diagram, we've got a virtual machine with multiple GitLab runner Docker containers. each configured to use a different Azure virtual machine as executors. These will be created and destroyed as necessary using Docker+Machine and the Azure driver. So when jobs are created and start running, it will create a Docker+Machine executor VM, and when the job's finished and the timeout's been exceeded, it will then destroy it. Configuring the GitLab runners to use the Docker+Machine executors turned out to be a fairly big task compared to what I was expecting. The GPU-powered virtual machines were the biggest challenge. With the added GPU comes added requirements for specific drivers to enable its use. We knew we needed to be able to use both TensorFlow and PyTorch. We experimented with the N series of virtual machines on Azure. They use the NVIDIA Tesla V100 GPUs. The easiest method I found of getting things to work as we wanted was to use the Azure Marketplace images, which helpfully NVIDIA provide themselves. I did attempt to provision some images myself using Ubuntu 18.04, but I didn't fare well with my initial attempts, and it seemed like a silly thing to waste time on at this point. To achieve the desired options for training during the POC, we needed at least 4 runners, 2 different GPU-powered executors, and the same number of CPU-powered executors. This would hopefully give us enough flexibility to experiment with different sizes for each model without constant changes to the configuration. With the runner registration, I'll start by saying the documentation's pretty good. Only so much of the runner configuration can be specified in the config template, and the rest needs to be specified during the registration. We quickly found that we were hitting limits on the number of runners which could be created on each virtual machine that were hosting these containers. We believe this is almost certainly because we were using the same machines as Docker-based executors for some deployment pipelines, and the issues appeared to be related to disk I/O. We were getting large queue depths, and we found that running more than about 6 jobs on a node, even using premium disks, which are supposedly able to support 600 IOPS, we were getting pretty poor performance, and jobs would often time out. Auto-scaling using either scale sets or probably more likely switching to Kubernetes are likely things that we'll look at in the near future. But for the initial stages, we went with a dedicated runner virtual machine just for the ML training jobs. Another thing to take into account at this point is Docker pruning. Will certainly need looking at, or you quickly run out of space. So I'll just quickly touch on some of the tools which we used throughout this project. Should hopefully give you a clearer picture of how we went about it and what prerequisites are needed to succeed. We heavily use Terraform for infrastructure management. We've had some issues with Azure. The Terraform feature compatibility is definitely lagging the web console, but by and large, we've been able to work around these issues and not use ClickOps. I know Azure are hard at work catching up on these differences, but I suspect with the speed new cloud features are released, I won't expect complete parity anytime soon. Ansible was used for configuration management and helped simplify and automate the process of registering all the different GitLab runners. We used Elasticsearch for logging, and we used Prometheus and Azure Log Analytics for performance metrics and alerting. This was used due to the sometimes short-lived executor instances. So Prometheus wasn't suitable, and we had to just use the built-in Azure monitoring and log analytics. GitLab Prometheus integration is certainly something we'll be looking into in the near future, but we didn't manage to try that at this stage. Dockerizing jobs was probably the area which I felt by far the most uncomfortable at first, but actually it turned out to be one of the areas where my help was required the least. I hope you can excuse the S rather than the Z in Dockerizing, but I'm British, so I can't help that. I was lucky that a few members of both the data engineering and data science teams had already been experimenting with Dockerizing some of their work. So with a little assistance, they were able to get things working fairly quickly. I'd suggest starting with a good set of example Docker files, which can then be easily copied and adapted as required. This helps with ensuring best practices are followed and often saves many issues and questions from arising in the first place. As we were being fairly security conscious, or I certainly was myself, one of my primary concerns I had was the source of base images which were being used by the teams. Docker Hub's full of perfectly good base images, but it's also known there are some bad apples on there too. Having a local set of known safe images stored on your Docker registry is definitely advisable. This can also help ensure that the base images being used only contain the required components and are thus as small as possible. Multi-stage builds are definitely something which should be considered too. This can save time, space, potentially make things more secure. The end result was that both the data science and engineering teams were easily able to create, train, and deploy new models. We saw significant reductions in training time for models. They were up to 20 times faster. We were able to train models both using Kubernetes for less intensive training jobs and Docker+Machine executors, both from the GitLab CICD pipelines. Issues have been reported much less since this project went through. I suspect this is largely down to much of the standardization of the work which was being done. Many of the data scientists and engineers have actually since progressed significantly with their cloud and DevOps utilization. We've seen a massive increase in the number of teams asking about monitoring for their models and services. We've also seen our usage of GitLab CICD mature significantly. We've had cleaner pipelines and better uses of all the other resources available on the platform during their pipelines. I'll start by admitting the title of this talk is perhaps a little misleading. The aim was never to reduce the operating costs too much, but to ensure that the unnecessary expenditure was reduced, whilst also improving the platform and tooling provided to the teams. The infrastructure cost savings of not running the workstations 24/7 are more than overshadowed by any training jobs which are running. In terms of total cost savings, I don't personally have any figures to hand, and it's certainly not where my expertise lie. But I think it's fairly safe to say that the time saved for the data scientists in battling to get insights is probably more than offsetting the additional infrastructure costs for the expensive training instances. And the next step that the data scientists are actually undertaking is to increase their knowledge and awareness of which insights are actually creating value for the business and where they should focus their efforts on next. Some Azure specific tips. One big one was the VM name character limit. I believe it's 64 characters. I wasted a not insignificant amount of time debugging why Docker+Machine was failing to provision infrastructure, and this turned out to be the culprit. We also experienced issues with Docker+Machine failing to delete virtual machines after the timeout had been exceeded and jobs had finished running. I'm unsure if this is an Azure issue, an Azure Docker+Machine driver issue, or a Docker+Machine issue, but wherever it came from, it was worth keeping an eye on, as having expensive machines running for hours without any jobs to run is not recommended. Availability of instances was a bit of an issue. I'm aware this has been exacerbated by COVID-19 with more companies moving to the cloud, but we actually experienced availability issues on Azure before this, especially with GPU-based instances. In the Amsterdam region, GPU-based instances were quite often unavailable in many sizes, and even for other instance types, we hit issues occasionally, although far less regularly. Spot instances probably won't work for this unless you've got very fast training jobs. The risk of your instance being unavailable and 2 minutes notice interrupting long-running jobs is probably undesirable. Reserved instances, unless you're running a large number of jobs 24/7, the credits don't get saved up when you're not using them, and you can't use them in parallel, so it's probably poorly suited. And the other thing to bear in mind is that disk I/O is also constrained by the VM size, not just the disk. So making larger disks won't necessarily help at a certain point for increased performance. The maturity of teams is going to be a very large factor in whether projects like this will succeed. Data science is not currently known for its universal acceptance of DevOps practices. I don't think that's right, and I believe any team can derive huge benefits from adopting DevOps practices and utilizing the cloud. I was very lucky to have a few members of both the data science and data engineering teams keenly involved from the start. And without buy-in from the team and business, projects like this have no hope of succeeding. It will be slow and disruptive at first. Working in an agile manner with data scientists and engineers committed to the project from the start is vital, and I wouldn't have got far without this. Regular meetings and communication with the team is something that really helped me personally. As with any area outside of your comfort zone, it's sometimes difficult to fully understand what needs to be done without regular opportunities to ask questions, and communication really is king. Thanks for watching my talk. I hope it's provided some inspiration, hopefully some useful information too for anyone embarking on this journey. If you've got any questions or comments, feel free to reach out to me. I'm available on Twitter, email, or feel free to connect on LinkedIn.